I think you have covered some of the quantum properties yesterday, if I'm not mistaken, but I'll just skim through at least two of them to keep and hold them at the back of our minds throughout the presentation. Although fully aware that I will barely scratch the surface of the inner complexities of quantum computing, but at least this is important to know. So superposition, what's that? And I think quantum waves are something that demand a sort of a stretch of the imagination to fathom their spooky nature. So imagine touching the surface of a pond at two different points. The ripples spread across the surface and eventually overlap, forming an intricate net of superpositions. The difference between bits and qubits is something that resembles slightly that, I think. Bits are based on, let's put it this way, qubits can represent numerous possible combinations of 1 and 0 at the same time. Qubits are the quantum elements, so the subatomic elements at the base, at the infrastructure of quantum computing, where bits are how traditional computers, so non-quantum computers, process and crunch numbers and process information and so on. So this qubits has this ability to be in multiple states at once. This is called superposition. While qubits can think either in 0 or 1, qubits can sort of circulate and be at two positions at the same time. This exponentially increases their capability of crunch numbers and process information at lightning speed. So this is, and how this is accomplished. Superposition is mainly accomplished by the manipulation of particles that are usually done with precision lasers and microwave beams. The second key property of quantum would be entanglement. So researchers can generate pairs of entangled qubits, which then share this single quantum state. Einstein referred to that as a spooky action at a distance. So entanglement is an emergent quantum property that arises when two particles, such as photons or electrons, are bound together and remain so even when separated by vast distances. It's as if the particles were able to somehow retain the memory of their original correlation, even as they drifted apart. I find this image very enlightening from Professor John Praskill, who is the Richard Feynman Professor of Theoretical Physics at the California Institute of Technology, who gave this very insightful analogy with a book. So it's as if each page holds a fragment of meaning, I'd say qubits, that only deepens as we turn each leaf. By the time we reach the final page, we realize that we have grasped a meaning that is not scattered across the individual pages, not as it dwell on each of them separately, but rather emerged from the entanglement of these pages, which coalesce into a holistic understanding. So a quantum weaving together that transcends the sum of its parts. So this way we can have a quantum system that stores a lot of information that cannot be traced back to component parts of it. And what does that mean precisely? Why, as I said, while computers think in bits, a stream of electrical or optical pulses representing either 1 or 0 at a time, these two properties combined exponentially increase the processing, these two properties, I mean, entanglement and superposition, exponentially increase the processing power and number crunching ability of quantum computers. And why this is important. So to put it mildly, let's say the cybersecurity architecture, the entire cybersecurity architecture of our data communications, essentially what underpins the global economy, is based on encryption systems that rely on the factorization of huge, massive numbers. And while it would probably take a good many years to factorize, let's say, a 600-digit number using classical computers, an enhanced quantum computer equipped with an algorithm like Shor's, and we'll briefly skim through that, some of the quantum algorithms available today, these computers would crack it in a matter of hours. So this puts the entire cybersecurity architecture of the web in jeopardy, right? And this, of course, sent governments into a race to transition to post-quantum cryptography, or PQC, and other quantum-resilient encryption methods, since governments are now banking heavily on the so-called Q-Day, which is a projection of when quantum computing is expected to become a reality, and that's around about 2030. So they're very, let's say, just around the corner. This is a visual representation of what would be a circuit design of Shor's algorithm. Shor's algorithm is a quantum algorithm, but it's not the only one. So surely the intricacies of these algorithms are impenetrable to me as a lawyer and trained in law and philosophy. But there are others. There are other quantum algorithms, such as Deutsch's parallel computing algorithm, or Grover's quadratic speedup, or an alternate database search algorithms. This is a visual representation of certain experiments that have taken place with applying these are simulations, right? Using quantum algorithms to develop watermarking techniques. This image on the right side is one from the IBM quantum experiment, where anyone can have access. It's a platform that can run experiments on this IBM quantum processor and experiment with watermarking techniques. So watermarking has been typically used for copyright protection by embedding author-related information into a signal or an image. Since 2012, new image encryption algorithms have begun to harness quantum information theory in image encryption, breaking new ground in quantum image watermarking. Now, quantum image watermarking technology is capable of embedding the quantum information related to the owner's identity into the quantum image. Using cloud-enabled quantum computing platforms like IBM Quantum Experience, displayed on the right side, or software like MATLAB, several methods combining quantum encryption techniques have been then proposed to achieve information steganography, which is a method of hiding information into another signal or another image, and quantum watermarking. A few results have been, for instance, I'm quoting here, this very insightful, a very complex paper published in the International Journal of Theoretical Physics, a quantum image encryption and watermarking algorithm based on QDCT and Baker-Map. As I said, this is, I'm just skimming through some of the theoretical fundamentals just for us to have a glimpse of how quantum computing and copyright actually interface. So this is for you to have, this is just a visual representation of what a quantum watermarking looks like. you see the copyright owner can embed the watermark image into the carrier image to ensure that the watermark image can't be detected. Also, again, referring to this paper, Quantum Watermarking Scheme based on INEUEQR, published in the International Journal of Theoretical Physics. So the left column, you have the carrier images. These watermark images are then embedded within those carrier images and then can be also extracted. And we can also, you can see here that the visual quality of the carrier image embedded with the watermark images is comparatively good. Right. So, how does quantum computing actually interface with copyright law? I think that there has been very little research on that score, but there is a very insightful paper by Dr. James Griffin, who lectures at the University of Exeter, and I'll display some of his very interesting findings and projections in that regard. So copyright works with embedded quantum watermarks will be more likely to be protected than those without such watermarks, because quantum-enabled computing power may see a much more granular reuse of elements of films, for instance, to create new content, scenes, characters, music, scripts, and we can expect an increased use of copyright management information techniques, exemplified by watermarks and filtering mechanisms, to detect and prevent copyright infringements. These techniques allow us to track and trace the way in which content is being used. Watermarking of digital copyright works has been vital to streaming services such as YouTube, Netflix, and Spotify, to name but a few. But users can be sure, and I'm quoting ipsis literis, users can be sure that the nature of quantum computing is likely to ensure that there is a breadcrumb trail of their activities in a way that has not existed with traditional digital computing. And that means that this quantum watermarking will be able to protect copyright material, copyright content, in a way that that materials without those watermarking cannot. This we can also we can see how this will generate certain externalities in terms of a discrepancy and a difference of level of protection favoring those equipped with the quantum technology to protect their content in contradistinction to those, as opposed to those who are bereft or lacking resources to protect their copyright material with quantum watermarking. Now, with that in mind, I will submit now a few suggestions and observations that might contribute to the debate about total innovations and what they actually mean. Now, since the early days of copyright, its shape and structure have always been attached to a subject, an individual, right? The right holder, the owner of an original expression as an individual right. Now, in an age of ever-expanding disruptive technologies, the legal architecture of copyright is drifting away from the copyright holder to the network itself, which marks a fundamental shift in the legal grammar of these rights. These changes wrought by generative AI, for instance, I'm quoting Sylvie Delacroix, the distinction between reading, for instance, and copying has all but collapsed in an age of reading bots whose copying is the necessary byproduct of their alleged capacity to read. Robotic readership has been accommodated under the fair use doctrine of an intermediate copy for non-expressive users. Note the anthropocentric logic of the term expressive that has been widely written about by Matthew Seg and Sylvia Delacroix, and this is in the that has spurred a hot debate in English-speaking jurisdictions about fair use doctrine, in the UK, the fair dealing. And in Europe, there are also debates about TDM exceptions and opt-out mechanisms. And we can also delve into that afterwards. This is an example of how the legal architecture of copyright has been shifting away from the individual, from subjective or individual rights, to the arrangement, to the structure of the network itself, with copyright materials stream or dwell. And we are now witnessing this digital erosion of the proprietorial structure of copyright, when we put it this way. This is perhaps an interesting trait or characteristic of a total innovation. And we might be shifting to a whole different legal framework, not based perhaps on ownership or fixed boundaries, but rather on technology-reliant rules of access or digital rights management mechanisms. We'll also discuss, for instance, the recent AI Act in Article 53, if memory serves, compelling or obliging generative AI providers to display a summary of the database, the training database used for these generative AI. This is an example of this detachment of the legal, again, of the legal architecture, of the legal structure, or the very grammar of copyrights from the subject, from the individual, to the network. I was promised 20 minutes, and I think I've covered this is what I had to say. And Professor Marina Teller, perhaps we might open the floor for questions now.
Many thanks for your talk.